Hi, hello, good afternoon. Welcome back. Okay, our this module is all about amplitude modulation part 2. Okay, so in this module, we will be discussing about different mathematical computations in usually used in amplitude modulation. So particularly the modulation coefficient, the voltage, power, and current distribution in an amplitude waveform. Okay, so to start with, we have here our AM modulator. So just a brief review from our previous video. So an AM modulator is a nonlinear device which has two inputs and one output. Okay, so what are those two inputs? So our two inputs are your carrier waveform or your carrier signal and our modulating signal. So usually our modulating signal is in the form of an audio, a video or data. Okay, so while our carrier signal is a sinusoidal waveform, typically produced by our oscillator. Okay, so our modulating signal is usually a low frequency from the low frequency ranges, from the audio frequency ranges, from the voice frequency range, while our carrier frequency is RF. So when we say RF, we are talking about radio frequency. Okay, so we have here one output. Our output is the AM modulated wave. Okay, so the information acts, so your VM, the information acts on or modulates your RF carrier, and the output is within what we call an AM envelope. Okay, so this is our representations for the two inputs and our output. So our input is represented by your audio signal or your information signal. So we call this a share VM for modulating signal. So this is a sinusoidal waveform. So with respect to time, instantaneous time. So we have here your EM, which represents the peak value. Okay, so EM is the peak value of the modulating signal. And then we have here, since it is a sine wave, so it is sine of 2 pi FM. So this is your modulating signal frequency with respect to time. Okay, so this is our carrier signal represented by EC, the peak value of the carrier signal. And then we have here another sinusoidal function. So this is sine 2 pi FC, wherein FC is the frequency of your carrier signal. Okay, so after passing through a modulator circuit, the output is your AM waveform. So this is your AM double sideband full carrier waveform. Within what we call the envelope. So the red lining is your envelope, okay? And our equation for our AM is we have here EC plus EM multiplied by sine of 2 pi FMT multiplied by sine of 2 pi FCT. Okay, so later on, we will be dealing on this. Okay, because using this equation, we will be determining the amplitude of your side waveforms or your sidebands. Okay? So usually, after passing through a modulator, we produce the sum and difference frequency, and in AM, we call this as the upper and the lower sideband. Okay, so we have here your amplitude modulation. So the first thing that we're going to discuss now is the coefficient of modulation. So the coefficient of modulation or the modulation coefficient in some other references is represented by small letter m. Okay, so coefficient of modulation is a term used to describe the amount of amplitude change present in an AM waveform. So when we say amplitude change, this is what we refer to as modulation. Okay, so we are modifying something, and what is that characteristic that we are trying to modify? So that is your amplitude. Therefore, we are modifying it. So therefore, we have an amplitude change. So the amplitude change, this is our modulation process. Okay, so big M, okay, is what we call the percent modulation. So the percent modulation is simply the coefficient of modulation stated as a percentage. Okay, so capital M, or the percent modulation, gives the change in the amplitude of the output wave when the carrier is acted on by a certain modulating signal. Okay, so to analyze this, okay, or to get the value for M, we have here M, or the modulation coefficient. This is unitless, and this is equivalent to EM divided by EC. So if you will be recalling our previous slide, so your EM is the peak amplitude of the modulating signal, while EC is the peak amplitude of your carrier signal. Okay, so it is they are both in terms of voltage, so it will be cancelled out, leaving our modulation coefficient unitless. Okay, so multiplying it by 100 gives us our percent modulation, or our capital M. Okay? So, what is the relationship among your M, or your coefficient, modulation coefficient, your EM, and your EC? Okay, so from our previous video, again, it is said that when we discuss about phasors, so we have here your maximum voltage, or Vmax. So this is the waveform if we're going to look at your waveform using an oscilloscope. So actually, we are looking at the analog signal, or the time domain signal for our waveforms. So we have here your Vmax. So positive Vmax is the carrier signal plus your modulating signal, while your Vmin here, positive Vmin, is your carrier signal minus your modulating signal. So we are having this type of waveform if the modulating signal is a pure single frequency sine wave and the modulation process is symmetrical. So what do we mean by symmetrical? Okay, so it is symmetrical when its positive and its negative excursions of the envelope's amplitudes are equal. So what we have on the upper side of your envelope is just the same as on the lower side of your envelope. Okay, so we have here your negative Vmax, so that is minus EC minus EM, and then we have your negative Vmin, that is minus EC plus EM. Okay, so in this when we are given the maximum and the minimum voltage, we can still solve for the modulation coefficient. For example, we are not given the peak EM and the peak EC. Can we still solve for the modulation coefficient? Okay, so I will be showing you the relationship among your M, your EC, and your EM. Okay, so I have here the derivation showing the relationships between the three. Okay, so from the waveform, we're going to see to it. Okay, so we said a while ago that your V maximum, okay, so your V maximum is equivalent to um the peak amplitude of your carrier plus the peak amplitude of your modulating signal, while your V minimum is the peak voltage, or peak amplitude of your carrier minus the peak amplitude of your modulating signal. Okay, so that will give us in terms of the V min and the V max, so that is EM, which is equivalent to 100 V max minus V min. Okay, so V max is EC plus EM minus EC minus EM. Okay, so your EC here will be cancelled out. Then we have here 2 EM. So 2 will be cancelled out, leaving us with the value EM equivalent to 1/2 V max minus V minimum. Okay, so when we are trying to measure it using an oscilloscope, sometimes in the given problem, instead of writing the equation, we are given the maximum and the minimum voltage. Okay, so that we can show the relationship between the peak values and your minimum and maximum values. Okay, so for EC, looking at the figure also, so EC is equivalent to 1/2 multiplied by Vmax plus Vmin. Okay, substituting this here, that will give you EC plus EM plus EC minus EM. So EM will be cancelled out. So that will give you 2 EC. So 2 divided by 2. Okay, so that will give you equivalent to EC. Okay, so where did this came from? So if you're going to look at the figure, so it came from the figure, and at the same time we are considering a symmetrical envelope. Okay, so but a while ago in our previous slide, we said that the percent modulation is equivalent to EM divided by EC. Okay, so this is EC times 100. Okay, so but what is EM? EM is equivalent to 1/2 multiplied by Vmax minus Vmin divided by what is EC? EC is equivalent to Vmax plus Vmin. Canceling your 1/2 here, that will give you your M, which is equivalent to Vmax minus Vmin divided by Vmax plus Vmin times 100. Okay, so this is your percent modulation. Okay, divide this by 100, you will be getting your small m, or when we want the percent modulation, so this is the answer. Okay, so this is when you are given the minimum and the maximum value that can be seen when you are using an oscilloscope. So you can solve for the modulation coefficient either using the peak values or using your maximum and your minimum values. Okay, so this is the showing the relationship between your M, EM, and your EC. So the peak change, okay, so the peak change in the amplitude of the output wave, which is EM, is the sum of the voltages from the upper and the lower side frequencies. Okay, so since your EM is just equivalent to the sideband, so the amplitude of your EM is equivalent to the sum of the amplitude of your two sidebands. And since we are talking about symmetrical waveform, since we are talking about symmetrical waveform, so that is equivalent to the amplitude of the upper sideband. So in our previous video, we just get the frequencies of the sidebands. We weren't able to discuss what will be the amplitude of those sidebands. Okay, so in this video, we are now ready to determine what is the amplitude for the two sidebands. So sa the modulating signal, the amplitude modulating signal is simply equal to the sum of the amplitude of the upper and the lower sideband. And assuming it is again symmetrical, so that will give us the lower sideband amplitude equivalent to the upper sideband amplitude. Then we have here your amplitude of the upper sideband, which is equal to the lower sideband. That is 1/2. Okay, Vmax plus Vmin divided by 2. Okay, because that will be divided between the upper and the lower sideband, giving us 1/4. Okay, of the Vmax plus Vmin, wherein EUSF is the peak amplitude of the upper side frequency, that is of course in terms of voltage also, and ELSF is the peak amplitude of the lower side frequency in terms of voltage. Okay, so we have here the figure showing percent modulation of an AM DSBFC envelope. So again, what is this? This is the conventional AM, or the double sideband full carrier AM. So showing here is the modulating signal, and then the unmodulated carrier. So we have here your two types of modulation index or modulation coefficient. So we have here a 50% modulated wave, and we have here a 100% modulated wave. Okay, so the ideal for AM is 100 percent modulation. So when we say 100% modulation, that is the peak amplitude of your modulating signal is equal to the peak amplitude of your carrier signal. Okay, so in this case, as you can see, your V minimum here is equal to 0, because if we subtract that, V minimum is equivalent to EC minus EM. That will give you 0, and your maximum is twice your EC. Okay, so the ideal value is 1. Okay, so these are the different conditions of coefficient of modulation. So M is a certain value which is usually between 0 and 1. Okay, so when your M is greater than 1, okay, so that will happen. So when will your M happen? So since M is equivalent to EM all over EC, your M will be greater than 1 when your EM is greater than your EC. Okay, so imagine we are placing your modulating signal onto the carrier. Okay, so we are assuming that at least the carrier has a greater amplitude compared with your modulating signal. So remember our analogy regarding the carrier and the modulating signal. So when you have to travel a long place, you may ride on a horse, right? So your horse is the carrier and the rider is the modulating signal. Okay, so what happens if the rider is bigger than the horse? Okay, so it would look awkward, right? Or just imagine you have a letter and you have to send that letter. You have to place that letter on an envelope, okay, in an envelope. So what will happen when your letter is bigger than the envelope? So we are assuming that at least, okay, the carrier has a greater amplitude compared with your modulating signal. So when your modulating signal has a higher amplitude compared with the carrier signal, so this will cause a severe distortion of the modulated waveform. So what we call here is we have a case of over modulation. And of course, this is distortion. This is considered as noise. So we do not want this. Okay? And this occurs if the amplitude of your modulating voltage is higher than the carrier voltage. Okay? So when your M is lesser than 1, of course, this is the usual, since the M is equal to 1 is an ideal and there's no such thing as an ideal. So whenever your modulation coefficient is nearing 1, that means we are nearing the ideal situation. But in reality, so your M is usually lesser than 1. Okay, so in AM, it is maybe around zero point 0.8 or something. Okay, so when your M is lesser than 1, no distortion will occur. Okay, so the amplitude of the modulating signal is less than the carrier amplitude. So this is the normal waveform for AM. And lastly, when your M is equal to 1, wherein we say that this is the ideal condition for AM. So this generates an output at the receiver without distortion. And as you can see, this is said to be ideal because there is no such thing as a perfect system, because once your signal is sent uh, in free space through free space, noise is inevitable, and that case alone um is a guarantee that we will be having distortion. So it just depends on our circuits and our filters and our tuned circuits how we're going to eliminate those. Okay, so therefore we do not expect much of an ideal condition, but we can safely make use of the ideal condition for theoretical analysis or for computational discussions. Okay. So we have here your AM voltage distribution. Okay, so we are now ready to identify what will be the voltage across each of the different sidebands. Okay, so we always say that your EM is lesser than your EC. So we are always assuming, okay? So we are always making sure that your EM is always lesser than your EC. So we have here your two equations. So your equation for the carrier and our equation for the modulating signal. Okay, what is your since your EM is lesser than your EC, the peak value of the carrier is the reference point for the modulating signal. Okay, so we are always assuming if this is the maximum carrier, so your modulating signal must use that as a reference. Okay, so the value of your modulating signal is added or subtracted to your um from the peak value of the carrier. So that's why we have here your V1 here. So we have here EC plus VM. Since VM is changing with respect to time, it is instantaneously changing. So we are adding and subtracting this. So we'll just consider adding. So we're going to add this instantaneously. Okay, so it is changing. The amplitude of your modulating signal is changing. So that change, we're going to add that to your peak carrier voltage. Okay, so we have here EC plus VM. So the instantaneous value of the modulating signal algebraically adds to the peak value of the carrier. So technically, what is our VM? So that is our whole modulating signal. It is varying with respect to time. Okay, so it is changing. So we have here your EC plus the varying, okay, or the instantaneous value of your modulating signal. Okay, so your V2 here is the complete modulated waveform. So your V2 here is the is equal to V1, which is this one. Okay, this EC plus EM sine of 2 pi FMT becomes now the new amplitude. Okay, so by substituting our V1 for the peak value of the carrier voltage. So, your Vmax will become the carrier voltage plus that instance when your EM is in its maximum location. So, therefore, this whole item here becomes the peak value of your carrier signal, and then it will become so that the carrier is EC. So this is now the new EC because the amplitude is now changing. So this is the maximum EC, and then we have to include again 2 pi sine of 2 pi FCT. Okay, so your VAMT now, or the equation for your AM signal now becomes EC plus EM sine of 2 pi FMT. So this is your entire V1, and then we have here your sine 2 pi FCT. So this whole thing here is the amplitude of your modulated waveform. Okay? So this EM here is the peak change in the amplitude of the envelope. And this is the frequency of the modulating signal. Okay, so the peak change in the amplitude at its specific frequency plus your EC, that will determine the amplitude of your modulated wave. So if we're going to look at a modulator circuit now, our information signal is this one. Okay, this is our information signal, and our carrier signal is this one. So what is now the output for our AM? So the output for our AM is this one. Okay, so as you can see, if we're going to distribute this one, so this is EC multiplied by sine 2 pi FCT. So what do we have there? We just have your original carrier signal. So remember when we discuss our discussion on the previous video, so the modulator has four outputs. So you have a DC, okay, so you have a DC voltage, and then you produce the carrier. So we produce the carrier. We just proved that we produce the carrier, because if we're going to uh if you're going to multiply this one, okay, so if you're going to distribute this, it will give you EC sine of 2 pi FCT. So what is EC sine of 2 pi FCT? That is your original carrier signal. And of course, you have the sideband. So what is the equation for your sidebands? If we're going to distribute this 2, okay, so it will become EM sine of 2 pi FMT multiplied by sine of 2 pi FCT. Okay, later on, we will be using a trigonometric identity when we have sine function. Okay, so when we have a sin function. So, okay, so relating this now to the modulation coefficient that we have discussed a while ago. So, we have here EM is equivalent to MEC. Okay, so M is equal to EM all over EC. So, EM is can be solved using M multiplied by EC. So, substituting that to your EM here, so this will give you EC plus MEC sine of 2 pi FMT sine of 2 pi FCT. Okay? So, factoring this out, factoring your EC, that will give you factoring EC sine of 2 pi FCT. So, this is 1 plus M sine of 2 pi FMT. Okay? Then we have here EC sine of 2 pi FCT. Okay? So, EC sine of 2 pi FCT, this is your unmodulated carrier. So, you have an unmodulated carrier at the output of a modulator. Take note, your carrier is still intact. Okay? So, with or without modulation, your carrier is still intact. Okay? And then we have here your constant, which is your 1 here. And then we have here your M sine of 2 pi FMT, which is your modulating signal. Okay? Why do we have here your modulating signal? Because of the factor M here. And M is the combination of your EM and your EC. Okay? So, this will be factoring this out. Okay, so factoring again the formula. So we have here EC, MEC sine of 2 pi FMT, sine of 2 pi FCT. So that will give you EC multiplied by sine 2 pi FCT. So this is your carrier signal. And then we have here MEC sine of 2 pi FMT, sine of 2 pi FCT. So if you're going to recall your trigonometric identity, so we have here sine A times sine B. Okay, so what is your A and B here? Your A here is your FM and your B here is your FC. Okay, or vice versa. So we can use FC as your A and FM is your B because of the sum and the difference, because FC is always greater than your FM, of course. Okay? So sin will give you cosine A minus B over 2 minus cosine A plus B over 2. So this is plus and this is minus. So this plus here signifies your upper frequency signal, and this minus here signifies your lower frequency signal. Okay? So, and then of course we have divide by 2. So our MEC here is equivalent to MEC divide by 2 cosine of 2 pi FC plus FM. So, our upper cutoff frequency FC plus FM, that is your upper side frequency. Okay? And our amplitude is MEC all over 2. So, the amplitude of your sidebands will technically be dependent on your modulation coefficient. So, it depends on your modulation coefficient. So, if your modulation coefficient is equal to 0, therefore, we don't have any modulation procedure process. So, we don't produce sidebands. Okay? So, the carrier signal is intact. So, that is your EC. That is your unmodulated amplitude for the carrier. Okay? And this is MEC all over 2. So, that explains why in our previous diagram, although we don't have yet a numerical value for the sidebands, but we have already drawn that your sidebands has somewhat smaller, okay, amplitude or voltage value. So that means because our M is always lesser than 2 or lesser than 1, so it's a decimal point, and any value multiplied by a decimal point gives us a lower value for our numerator. And then we divide it by 2 further, so therefore we are expecting a lesser voltage amplitude for the sidebands. Okay? So this is how your voltage is being distributed to the carrier and to our lower and our upper sideband. Okay? So next is your AM power distribution. Okay, so AM power distribution is the power dissipated is equal to the voltage squared divided by the resistance. Okay, take note of the RMS value here. Okay, so RMS value, um we since we're talking about power, we have to get the RMS value. So EC, if you're going to remember, EC is a peak, okay, or a maximum value. So to get the RMS value given the peak value, we have to divide it by square root of 2 or multiply it by 0.707. So power is given by voltage squared divide by R. Okay? So the power dissipated by the carrier is equivalent to the RMS value of the peak value of your EC. So EC is your peak. So therefore, we have here 0.707 to get the RMS value. So 0.707 of EC squared divide by R. Okay? So this is 0.707 squared. So that is 0.5 or 1 half. So the carrier power or PC carrier power, of course, in terms of watts, is equivalent to EC squared divided by 2R. Okay? So, this is the power at the carrier. Okay? So, this is the power in an unmodulated carrier. As you can see, you don't have modulation coefficient there. You don't have M. And when M is missing, of course, modulation didn't happen. So this is the power in an unmodulated carrier. Okay, if you're asking, what about the power on the sidebands? Of course, we have here your upper and lower sidebands. Okay? So, the power in the lower sideband is just equal to the power at the upper sideband. And that is equivalent to the peak volt. So if you're going to remember, MEC, that is the peak. Okay? So, that is your peak voltage of your sidebands. Okay, so we have to get the RMS value. So how do you get the RMS value? So you multiply it again by 0.707, then we square it. Okay, so that will give us, M squared EC squared divided by 2R. Okay, so like what we did earlier. Okay, so the M, so your amplitude for the sideband is equal to MEC. Okay, so that is MEC all over 2, right? So this is a peak value. So how do you get the RMS value? So you multiply this by 0.707, then you square it. That's why you have there all over 2. Okay, so you have your M squared, you have your EC squared, divide by, okay, so divided by, so this is 2, this is 2, then you have here another 2, so that will give you 4. Okay, so that will give you 4. Okay, so we have here, so you have another, so this is squared, your 2 here will be squared, that's why it became 8. Okay, so we have here, So always remember that this is a peak value. So we need to get the RMS value for this. And the RMS value is given by m squared PC all over 4. Okay? So this will give you m squared over 4 EC squared all over 2R. Okay? So EC squared all over 2R. So, simplifying this, that will give you the upper sideband, which is equal to the lower sideband, which is equivalent to 4 m squared PC all over 4. Why? Because EC squared 2R is equivalent to the unmodulated power, this one. So, this is it. So, we just substitute it with the PC, okay, or the carrier power. Okay, so you have to remember there that for a modulation coefficient equivalent to 0, okay, so for a modulation coefficient equivalent to 0, the power in the upper and the lower sideband is equal to 0. So as you can see, unlike in the carrier, it is dependent on M. So if M is equivalent to 0, therefore no power is dissipated by the upper and the lower sideband. Okay? So the total transmitted power is simply the carrier power. Okay? So if we wanted to get the total power in an AM double sideband full carrier envelope, we just add the 3. So what are those things that we are adding? So we just add the total transmitted power, that is your PT, that is equivalent to PC plus, or the power at the carrier, plus the power at the lower sideband, plus the power at the upper sideband. So substituting our earlier formulas, so you have PC plus, we have here m squared PC all over 4 plus MCP P squared, M squared PC over 4. So the total transmitted power is equivalent to PC plus M squared PC over 2. So it is M squared PC over 4 when we are talking about each sideband. If we're going to get the total sideband power, so it is equivalent to M squared PC all over 2. Okay? So, factoring out your PC or your carrier power, that will give you PC multiplied by 1 plus M squared all over 2. As you can see, class, the carrier power is not, what do you call this? The carrier power is unaffected by the modulation process. Okay? So, carrier power is not affected by the modulation process. Even though we make this equal to 0, still, your total transmitted power is the carrier power alone. Okay, but the total power in an envelope or in an AM envelope is increased with modulation. So as your M here increases, okay, likewise, the total power here will also increase. So, for a power spectrum, this is the power spectrum for a 100% modulation. Okay? So, if this is equivalent to 1, technically, each sideband will get the one-fourth of the power of your carrier, okay, if M is equal to 1. Of course, since M is not always equal to 1, since it is already the ideal value, so we expect a value which is lower. Okay? So, what is the implication of this, class? So, this shows the greatest disadvantage and the greatest advantage of your AM, of your double sideband full carrier or your conventional AM. So, what do we mean by that? As you can see, where are your information? Of course, the carrier doesn't includes any information. So, the information lies on the sidebands because there is your modulating signal. Remember, your information is your modulating signal, and your modulating signal is only seen at the sidebands. There is no modulating signal at the carrier. Okay? So, the information is contained in the sidebands, but most of the power is in the carrier, and the carrier has no information. So it means that the important thing wherein you have your information, it has a very very small power. So therefore, most of the power is wasted in the carrier, and that is the one big disadvantage of a conventional AM. Okay, so later on we will be discussing other types of AM. Okay, so we will see how are we going to deal on this type of disadvantage. But okay, this on the other half does allow for the use of a relatively simple, inexpensive demodulator circuits in the receiver. And what does that mean? So it means this is naman an advantage for an AM. Because of this setup, it allow for the use of a relatively simple and inexpensive demodulator circuit. So this is naman one of the major advantage for AM. It doesn't need a complex receiver for you to receive a conventional AM signal. Okay? So we're done with the voltage distribution, and then this is the power distribution. Okay, what's next? Another thing Okay, another thing with amplitude modulation is of course current. Current is also an important factor. Okay, so with AM, it is very often necessary and sometimes desirable to measure the current of the carrier and modulated wave and then calculate the modulation index from the measurements. Okay, so the measurements are made by simply metering the transmit antenna current first with modulation and then without the presence of modulating signal. Okay, so we compare what is the current when there is a modulating signal and then what is the current when there is no modulating signal. Okay, so for AM current calculations, we have here the total transmitted power is equivalent to the total current, okay, squared multiplied by R. So this is your power formula in relationship with your current, and then we have here your PC. So the power at the carrier is equivalent to the current at the carrier multiplied by the current of the carrier multiplied by R. So this is equivalent to, so since we are considering impedance match system, so if you still recall what is an impedance match system, we use the same resistances. So therefore, throughout the system, so we can cancel out your R there, considering an properly impedance system. So that will leave us with IT squared all over IC squared. Okay, so that will give you IT all over IC squared. Okay, so PT all over IC, going back to our previous formula, so PT is equal to PC multiplied by 1 plus M squared over 2. So putting your PC here, what do you call this? Transposing your PC here, that will give you PT all over PC is equivalent to 1 plus M squared all over 2. So IT all over IC now is equivalent to, so we squared this. So this is squared. So to eliminate your squared, we get the square root of this. Okay, so to get the total transmitted power, that is equivalent to the carrier current, and that is in amperes, multiplied by 1 plus M squared all over 2. Again, this is your IC is unaffected by modulation. Okay, so that is your current without modulation, and then your M is your current with modulation. So in real life, we can usually measure this. Okay, so the measurements are made by simply using ammeters or meters in the before the antenna. Okay, so in the transmit antenna. Okay, so we have here modulation by a complex information signal. Okay, so in our previous discussions, we are only considering, okay, so we are only considering single modulating signal waveforms. Okay, so our modulating signals that we are considering are just a single frequency. But in reality, class, in practice, okay, modulating signal is very often a complex waveform. Just the voice, okay, voice is not um is not composed of just a single frequency. So sometimes it is loud, sometimes it is quiet, so that means your amplitude is changing. Sometimes it is fast, sometimes it is slow, so your frequency is changing. So voice is a complex waveform. So in practice, in reality, modulating signal is very often a complex waveform which is made up of many sine waves, okay, with different amplitudes and frequencies. Okay, so in that case, each modulating signal, okay, will cause two sidebands. So therefore, if you have two modulating signals, you have four sidebands. If you have three modulating signals, you have six sidebands, and so on. So always remember that each modulating frequency will give you additional two sidebands, one of the upper and another the lower. And each frequency has its own amplitude, its own frequency that will give you its own modulation coefficient. So therefore, if you have three different waveforms, if you have three modulating signals, you have M1, you have M2, and you have M3. And then your AM waveform will be equivalent to FC minus FM1, FC minus FM2, FC minus FM3. And then on the other side, FC plus FM1, FC plus FM2, FC plus FM3, and so on. So that means we are expanding our bandwidth. So you have to remember always that in an AM transmitter, care must be taken to ensure that the combined voltages of all the modulating signals do not overmodulate the carrier. Okay, so since you are increasing and you are adding your EC, so you do not have, you must not exceed your EC or your peak carrier amplitude. Okay, so that's it. Okay, so let's have some examples. Okay, for our example number one, it says here, a modulated carrier wave has a maximum and minimum amplitude of 750 millivolts and 250 millivolts. Okay, calculate the value of percentage modulation. So as I've told you, our problems here in amplitude modulation topics are very simple. Okay, so this is we know that M is equivalent to EM over EC, but we are not given the amplitude for EM all over EC. Rather, we are given the maximum and the minimum value. So the answer there, okay, so the solution there is very simple. So we have there your Vmax is equivalent to 750 millivolts and your Vmin is equivalent to 250 millivolts. Okay, so what is your percent coefficient? So that is Vmax minus Vmin. So we just have to substitute this to our formula. So we have your Vmax minus Vmin all over Vmax plus Vmin multiplied by 100. Okay, so that will give you zero point 0.5, or that will give you, okay, so that will give you 50%. So as simple as that. Okay? So, second example, a 10 megahertz sinusoidal carrier wave of amplitude 10 millivolts is modulated by a 5 kilohertz sinusoidal audio signal wave of amplitude 6 millivolts. Find their frequency components of the resultant modulated wave and their amplitude. So, on our previous video, we have discussed the frequency spectrum, but on that case, we do not include yet the amplitude of the sidebands. So now we can include the amplitude of our sidebands. So how do we compute for this? So in this case class, so let us write the given. Okay, so the given are, so the given are as follows. So we have here your FC, that is 10 megahertz. Okay, so this is your carrier frequency. We have here your carrier amplitude, that is 10 millivolts. You have here your modulating frequency, this is 5 kilohertz, and our modulating peak modulation, modulating voltage equivalent to 6 millivolts. Okay, so your output waveform consists of three frequency components. So what are those three frequency components? So you have your original carrier frequency, which is equivalent to 10 megahertz. Okay? And then you have your upper side frequency. So your upper side frequency is simply the sum of your carrier and your modulating frequency. And that will give you, okay, so that will give you 10 megahertz plus 5 kilohertz. Okay, so that will give you 10.005 megahertz. And then the third frequency is your lower side frequency. And that is the difference between your carrier frequency and your modulating frequency. So that will give you 10 megahertz minus 5 kilohertz. So that will give you 9.995 megahertz. Okay? So the amplitudes, so we have an additional amplitude. So we said that the amplitude of the lower sideband is just equivalent or just equal to the amplitude of the upper sideband. And it has something to do with the modulation coefficient. Okay? And it is given by M multiplied by EC divided by 2. So this is from our voltage distributions. Okay? Topic. So how is voltage being distributed with your AM frequencies? Okay, so we need to solve for M first. Okay, so we can solve for M. M is equivalent to the amplitude, peak amplitude of your modulating signal divided by the peak amplitude of your carrier signal. So this is 6 millivolts divided by 10 millivolts. So that will give you 0.6. Okay, so substituting your 0.6 here, each sidebands, okay, each sideband will give you 0.6 times 10 millivolts divided by 2. So each sidebands will have 3 millivolts as its amplitude. Okay? So if you're going to draw the spectrum, your spectrum will look like this. So this is your spectrum. So this is your carrier with its unmodulated voltage. So this is 10 millivolts, and then your two sidebands here, and that is that they have both 3 millivolts as their peak value. Okay, so you may get the bandwidth. So although it is not asked in the problem, so we can solve for the bandwidth. So this is your bandwidth. Okay, so if we can subtract that, so your bandwidth is equivalent to 10.005 megahertz minus 9.995 megahertz. So that will give you 10 kilohertz. Okay? Or it is said that your bandwidth also is 2 times FM max. So your FM is equivalent to 5 kilohertz. So 2 multiplied by 5 kilohertz. So that will also give you 10 kilohertz. So the problems in AM is just as simple as that. Okay? So let's proceed to the third problem. So it says here, An audio signal is given by 15 sine 2 pi 2000 t. Amplitude modulates a sinusoidal carrier wave 60 sine 2 pi 100,000 t. Determine A, the modulation index, B, the percent modulation, C, the frequency of the signal and the carrier, and D, the frequency spectrum of the modulated wave. Okay, so how do we solve for that? So that case, we have here the equation. So the equation for our carrier is given by 60 sine of 2 pi 100t. Okay, so if you're going to remember, this is 2 pi fmt, right? Fc rather, fct. So therefore, this is your frequency. Okay? And then for the modulating signal, it is 15 sine of 2 pi. So this is fmt. So this is your FM. Okay? So, if you're confused, where is the carrier there? Okay, so where is the carrier there and where is the audio signal there? So although it is said in the problem, it is mentioned in the problem that that is the audio and this is the carrier wave. Always remember that the one which has the higher frequency is the carrier and the one which has the lower frequency is the modulating signal. Okay? And of course, from the equation, we can see their peak value. So this is your EC and this is your EM. Okay? So by substitution, our small m here is EM all over EC. So this is 15 all over 60 that will give us a modulation coefficient of 0.25. Okay, so this is quite low, but this is acceptable. Okay, so what is not acceptable is an over modulation. Okay, so when the value is between 0 and 1, so it is acceptable. Okay, so for the percent modulation, all you have to do is to multiply this by 100, so that will give you 25%. Okay, so we are asked for the frequency and no need to solve. So just by inspection from the equation, so we know that your carrier frequency is 100,000, or we can write that as 1,000 kilohertz. And then your FM or your modulating frequency is 2,000, or we can write that as 2 kilohertz. Okay, so the frequency spectrum, how do we draw the frequency spectrum? So this is your carrier with a voltage with an amplitude of 60 volts. So it's not mentioned in the problem that it is volts, but automatically it's a voltage class. So this is at 100 kilohertz. So your upper frequency is 102. So where did we get 102? This is the sum of your carrier and your modulating frequency. Where did we get 98? So it is the difference between 100 and your 2 kilohertz. Okay? And then where did we get 7.5? So that is the amplitude. So the upper and the lower side bands amplitudes are equal, and it is equivalent to MEC divided by 2. So this is 0.25 times. So this is 0.25 times 60 divided by 2. So that will give you 7.5. So in the spectrum, we just didn't draw the frequency at the same time. So we also included the amplitude. So this is the complete frequency spectrum for our waveform, for our AM waveform. Okay? So very simple. Okay? Our next problem, we have here a bandwidth of 15 megahertz of is available for AM transmission. So if the maximum audio signal frequency used for modulating the carrier is not to exceed 15 kilohertz, how many stations can broadcast within this band simultaneously without interfering with each other? Okay. So in this case of in this type of problem, we are given the bandwidth for the entire. So we are given the bandwidth for the entire channel. Okay, so for the entire channel, the bandwidth is supposedly 15 megahertz. Each FM station has a modulating signal of 15 kilohertz. So we know that the bandwidth requirement is equivalent by each station is equivalent to 2 multiplied by the maximum modulating signal. So in this case, the maximum modulating signal is 15. So what is the required bandwidth for this? So the required bandwidth for this is 2 times 15 kilohertz, which is equivalent to 30 kilohertz. So in this case class, the number of stations that can occupy the 15 megahertz bandwidth is simply 15 megahertz divided by 30 kilohertz. So that is equivalent to 500 AM stations. Now, in reality class, in practice, this is not really 500. Okay? Because if our spectrum is this one, okay, if this is our 500 spectrum, each will get 30 kilohertz. So each station will get 30 kilohertz bandwidth. Okay. However, if our circuits, if our electronic transmitter, for example, if our circuit is not very effective, okay, what happens is this station B might interfere with station C, and so on. So what do? We always place what we call a guard station. Okay? So in practice, in reality, if this is one radio station, okay, therefore, this and this is not permitted. So the next station is your this one. So this will be your station 1, this will be your station 2. Because the previous or the center stations here will serve as a guard station. Okay, so that when our filters, for example, or our tune circuit is not exact, there's the possibility of interfering with other station is wider. Okay, so we usually have a vacant slot. So technically, the stations are in their alternate modes. Okay, so remember that. Okay, let's have another example. In a broadcasting studio, a one this is a 1000 kilohertz carrier is modulated by an audio signal of frequency range 100 to 5000 hertz. So in this case, we are not just using a single frequency modulating signal. Okay, rather we have a complex waveform ranging from 100 to 5000 hertz. Okay, so the maximum is your 5000 and the minimum is your 100. So we are asked to find the width or frequency range of sidebands, the maximum and minimum frequency of the upper sideband, the maximum and minimum frequency of the lower sideband, and the width of the channel. Okay, so previous examples, we just have a upper sideband frequency and lower sideband frequency. So why is that? Because we only consider a single modulating frequency. So the difference in this example is that we have a range or a complex wave wherein it is composed of several frequencies. Okay? So how do we solve for that? First, let us get the given. So our FC here is 1000 kilohertz. Our modulating signal here ranges from 100 to 5000 hertz. So what is the width of your sideband? So the width of your sideband is from the highest frequency, modulating frequency, to the lowest modulating frequency. So each sideband, the lower and the upper sideband, has a width or a bandwidth of 4900 hertz. Okay? So the upper sideband maximum is equivalent to 1000 kilohertz plus 5 kilohertz. That will give you 1005 kilohertz. And the upper sideband minimum is equivalent to 1000 plus zero point 0.1 kilohertz. Okay? So that will give you 1000.1 kilohertz. So why both plus? Because they are both on the upper sideband. And upper sideband is equivalent to FC plus FM. Okay? So for the lower sideband maximum, so that will give you 1,000 minus 0.1. Okay? So that will give you 999.9 kilohertz. And then for minimum, we have 1,000 minus 5 kilohertz. So that will give you 995 kilohertz. Again, why 2? Because of the minimum modulating signal and the maximum modulating signal. So the width of the channel is the most the leftmost the rightmost frequency, which is the maximum upper sideband, which is 1005, minus the leftmost or the FM lower sideband minimum, which is the 995, and that will give us 10 kilohertz. Okay, so showing the spectrum now, we don't have just a frequency here but a band of frequency. So this is from 1.001 kilohertz to 1005 kilohertz. The bandwidth is 4900, and this is from 995 to 999.1. Again, the bandwidth here is 4,900. Okay? So, getting the bandwidth, this one, we have 1,005 kilohertz minus 995 kilohertz. So, this will give you 10 kilohertz. Okay? Other way of solving for the bandwidth, this is 2 times the maximum modulating frequency. So from 100 to 500 hertz, what is what maximum there? Of course, the maximum there is 5,000. So this is 2 times 5,000. So this will give you 10,000 kilohertz. So for the bandwidth. Okay, so this is how your spectrum will look like if you have a complex waveform. Okay? Next example. So the tuned circuit of an oscillator in an AM transmitter uses a 40 microhenry coil and a 1 nanofarad capacitor. If the carrier wave produced by the oscillator is modulated by an audio frequency up to 10 kilohertz, calculate the frequency range occupied by the sidebands and the channel width. Okay. So in this case, we are given the modulating frequency, which is equivalent to 10 kilohertz. Okay? So we don't have the carrier. So the carrier will still be produced by your oscillator. And since this is an LC oscillator, the resonance frequency of your oscillator will be the carrier frequency. So we are still to solve for the carrier frequency. Okay, so the carrier frequency for any LC oscillator circuit is equivalent to 1 all over 2 pi square root of LC. So substituting your L, 20 microhenry, this is microhenry multiplied by 1 nanofarad. So micro is negative 6, nano is negative 9. Okay, so that will give you a carrier frequency of 796 kilohertz. So your upper sideband frequency is equivalent to FC plus FM. So that is 796 plus 10. That will give you 806 kilohertz. And the lower sideband is 796 minus 10 kilohertz, which is 786 kilohertz, giving us a frequency range from 786 to 806 kilohertz. Okay, so subtracting this, 806 minus 786, so that will give you 20 kilohertz, or the bandwidth is also equivalent to 2 times the maximum modulating frequency. Since we only have one modulating frequency here, so that is 2 times 10 kilohertz, likewise will also give us 20 kilohertz. Okay? So in this type of problem naman, carrier is not yet given, but we are given an oscillator circuit. So we need to solve first for the carrier, but other part of the problem is very, very simple. Okay, so we're down to our last problem. So the total power content of an AM wave is 2.64 kilowatts at at a modulation factor of 80%. Determine the power content of the carrier in each sideband. Okay. So we have here your solution. So we are given your total power to be 2.64 kilowatts and our modulation coefficient is zero point 0.8. So this is from the 80%. Okay? So the total transmitted power is equivalent to the carrier power multiplied by 1 plus m squared all over 2. So this is just a direct substitution, but in this case, we are given the total transmitted power, so we need to solve for the carrier power. So the carrier power is simply the transmitted power divided by 1 plus m squared all over 2. So substituting that, 2.64 kilowatts divided by 1 plus zero point 0.8 squared all over 2. So that will give you your carrier power equivalent to 2000 watts. Okay, so how do we determine the power in the, okay, dissipated by the side bands? Okay, so the power from the side bands is equivalent to, so they're just equal, okay? The power at the upper sideband is just equal to the power at the lower sideband. And that is equivalent to m squared PC all over 4. So we're done solving for PC, okay? Zero point 0.8 is given, so zero point 0.8 squared times 2000 divided by 4. Okay, so the upper sideband, which is equal to the power of the lower sideband, is equal to 320 watts. Okay, so this is the power spectrum for the AM in our example. So the carrier receives 2 kilowatts out of the 2 point out of the total power, okay, which is what's that? What's the value of the total power? 2.64. Okay. And only 320 is within the sidebands. So imagine, where is the information? Here are your informations, and yet they receive a very, very small portion of the total power transmitted. Okay? But anyways, that's it. Okay? I think the computations for AM is very, very simple. Okay? So all you have to do is to understand, okay, the formulas and how did we get the formula. Okay, so if you forgot that, you can always make the derivation. Okay, so there's a set work here for your activity. Okay, so you have to do this during your asynchronous time. Okay, so thank you very much for listening. Okay, thank you very much for listening, and don't forget to like the video. Okay, so take care, thank you, and God bless. Okay, bye.